Alright, hey guys, welcome back to another episode of Intelligence Maxing. So, this episode gonna go over the deep learning challenge for image segmentation. I think yesterday we started just by going over some of the basics here, understanding what libraries we need, also what data we're using and how to interact with the data loaders for PyTorch, and also how to interact with the dataset. And then next we looked at the basic architecture of this neural network called the UNet. And I guess this is the standard for image segmentation type of architectures. So this is where I got a bit confused because looking at this photo, it's pretty complex. There's a lot of different layers from convolution layers, and then you have ReLU activation, then you have the idea of pooling, and then you have an upward convolution, and then dropout, then copying, and a one-by-one convolution in sigmoid. So there's a lot of stuff here that is pretty complex. Okay, I don't see... Oh, you know what? I think I need to go to... Oh, here we go. Yeah. So this is what we've changed so far. So I try to replicate maybe a simpler model for this. First by doing a convolutional stage, and then another convolutional stage, and then a one-by-one convolution. And each stage will increase the number of channels, so this one will have an output channel of 16 using a kernel size of 3x3, and this will have a kernel size of 3x3 as well, and we'll keep the same number of input and output channels. So last time we stopped, I believe we just finished implementing the forward pass. So in our input layer, we have flattened our input, our 256 by 3. And I'm going to double check to see what the size is of our input vector, just to make sure that it's exactly what we wanted. The second part is the first convolutional stage. So this will take in the flattened input, and after that it will output and be fed into a ReLU activation function. So this is the first, we'll call a convolutional stage, and then this is the second convolutional stage that takes okay, I guess another way of saying it is downsampling and upsampling. Downsampling as in you're decreasing the dimensionality, the spatial dimension of our image, and upsampling means that we're increasing the spatial dimension of our image. The last step is a one-by-one convolutional stage that will decrease the number of channels so that it's exactly equal to one channel. Now, in this photo, they have one single channel. I don't know what it's supposed to be because my impression was this input picture that we have is 256 by 256 by 3, and if we flatten it out, this is 256 squared, and then this is only a single channel though. Would we not have to do 256 squared times 3 in order to get the number of Actually, no, I don't think so, because we could have a 3x3. I see. We could have a 3x3 filter that will... Okay. Okay. Let me try to think here. Let me try to think. So if we could have a, let's say, 3x3 filter kernel, apply it as a convolution so that the number of output channels is 1 and the dimension is 1. Okay. So maybe this is not the thing we need to do actually to flatten our input. What we need to do is make a convolutional, we'll call this input stage. So we'll call this the inputs, and then we'll call this the output. By squared by 3, by 1. Self dot input stage is equal to, we'll do dot conv 2d, and then we'll do in channels is equal to 3, and then out channels is equal to 1. Kernel size, let's do 3x3, and I think in order to get the same exact amount of, in order to get the same dimension, we would need to figure out what padding and what stride we would need. Oops. Okay, you know what? Now that I'm thinking about it, I don't know if this makes a whole lot of sense. So let's just take a look at unit architecture. I see. So, I guess unit used a grayscale. Picture so it has a single channel. Coder block. So maybe we don't actually have to flatten anything. Okay, let's see. If that's... Okay, wait, we might need to run all. Runtime. Let's see if we can use T4 GPU. So criterion is equal to neural network dot binary cross entropy loss. Optimizer is equal to stride. Okay, so I think what we need to do is model that train. So we would have to take an image. Okay, I'll create a function actually. So def gets maybe define that here. Gets image. We'll call this mode is equal to train. Save your changes. Okay. So if mode is equal to train, then we'll do this. Oops. Oh shoot, okay. So else if mode is equal to val, then we'll get a new validation image. Then else elif mode is equal to test. Alright. And then we'll return the image mask. Turn image, or we can return none. Okay, so we will then image mask is equal to gets image. We'll do mode is equal to train. Okay, and then we would probably want to input this image into, so do forward. Oh, model dot forward line G. And I think K loss is equal to criterion. And then maybe we pass in the, so outputs, maybe prediction. So we'll see NN dots BCE loss. So prediction, then mask, right? And then okay. What's that? Backward. Optum dot step. Step optum at 0 grad. Okay, so this is resets gradient. So I think in this case, right now what we have is a, I guess you could call it a single batch, so one batch training example. Alright, let's take a look at loss is equal to empty. $64, $48, $24 split. Ah, I see. Okay, so there's 168 training, 48 validation, 24 testing images. Okay. Let's just see if this causes any error. I'm nervous. I'm nervous. I'm nervous to see if this is gonna work. Oh. Run after. Just grass. Okay. Okay, so shit. This is gonna be a problem. Column 2D received an invalid combination of arguments. Got ND array, parameter, tuple, tuple, int, but expected one of tensor input, tensor weight, tensor bias, tuple. Wait, print type image. Wait, image type. I'm not entirely sure what's going on here. All right. Okay, so what if I then did? How do I? Let's see. How to create tensor from NumPy array. PyTorch. Oh, torch from NumPy. So image is equal to torch dot from NumPy image tensor. I'm assuming that the mask is also going to be mask tensor. All right, let's see. All right, that's tough. We're making some progress here. Also, let me print the loss. Shit. To have 3 channels, but had 256 channels instead. on forward. Groups is equal to 1. Expected input 1, 2, 56, 56, 3 to have 3 channels, but okay, let's print input.size, input size. Okay, 256, 256, 3. We lose 1 size. This dimension stuff is pretty difficult. Okay, so it's not even getting to that point. All right. So we have a 256, 256 by 3. So do we have to transpose this then? I'm gonna take a look at this, see what ChatGPT says. Is this error mean in PyTorch? Okay, so I might need to permute. Might have to swap it. All right. Permute 2, 0, 1. Wait, what? Input type torch.float tensor and weight type torch.cuda.float tensor. Should be the same, or input should be mkld and tensor and weight is a dense tensor. What does this mean? To CUDA, maybe? Okay, nice. 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 Turn image array from data loader to tensor and store on GPU. Okay. Output size. Alright. Okay, so there's an error here where I think, alright, yeah, it's going from 256 to 128 to 128. But the size should be higher, I think. AKA, it should be... what should it be? I think 256. So how do we get 256 then? Padding is equal to stride is equal to 2. I think we're gonna need to pad the shit out of this. Oh, column 2D transpose, right? So maybe I'm not entirely sure how this column 2D transpose works. Transpose 2D work. Okay, so it seems like ChatGPT says that whatever this is, the conv transpose 2D, the use we're using it for is correct. It's useful for actually increasing the dimension, the spatial dimension of our image. How it actually does that is a bit confusing, not gonna lie. It's not super clear. But we're on the right step. Huh. Conv transpose 2D. Oops, shit. So times stride. Oh, okay. We might need a increase the stride to 2. Ooh, okay, so -1. Take a picture of this. Then add this here, so we have conv transpose 2D, and then we'll put that baby here. Yes sir, yes sir, yes sir. Okay. And then this one should be the conv 2D. Alright. Oh, I see that this isn't a full thing though. Great. What if I just copy and paste this then? Nope. How do I do a function? Alright, I guess there's no LaTeX. I feel like this is probably the same. Okay, I think this is good. So we take the just delete this, delete this. Okay, so we take the input dimension, subtract 1, multiply by stride. So the input dimension is going to be 127 multiplied by 2. Then we get 127 times 2 is 254 minus 2 times padding. Padding is 1 plus dilation times kernel size minus 1. So we 256. Oh, I see. Plus 1. So what if we did a kernel size of 2? So we have 2 by 2 minus 1 Yeah, that should work. So we decrease the kernel size by 1. Then we should get 256. Nice. So we do get 256. Alright. So we have none type has no attribute size. Oh, shoot. Okay. So we need to return the output. Oh, actually, sorry. I need to do a sigmoid first. So then we do print conv3 output is equal to f dot sigmoid. And then we have conv2, conv3. Okay, and then we return the output. And let's take a look. That's different from the input size. Okay, I think I'm gonna need to do this. Permute. Let's go. We got the loss. Let's go. Okay. Oops. Oops. Okay, there is no step. Optimizer dot step. Maybe. Okay, shit. I think it stopped. But it doesn't seem like the model is really learning anything. Because it seems like the loss is just constant. I'm starting to understand kind of what this is doing though, because I think what it's doing is it's just taking the background, which is the sky and grass, and what it'll do is in this binary segmentation, you're just trying to distinguish between what's the background and what's the foreground. So these are the objects of the buildings, whatnot. And the reason we're using sigmoid is to differentiate between what's actually background versus foreground. Okay, I'm gonna, let's see, 2%. All right, I gotta charge my computer and I also gotta go pee, so I'll be back. Okay, nice. I'm back, I'm back, I'm back, I'm back. Trying to find my headband, my headband. Where the hell's my headband? My headband. Okay. So I think then what I'll do is I'll oops. Do what's it called? Train to val. Oops. Train image tensor, train mass tensor. Then we'll do val image tensor, val image tensor. Then we could do, I think we could just do this. Okay, we'll do the val image tensor, and then what we want is the val mass tensor. Okay. So then this should work. Okay, nice. Nice, nice, nice. Nice, nice, nice. Alright. So, our thing is not doing shit. That's unfortunate. Train loss. Val loss. Yeah, our thing is not doing anything. Alright. I wonder, what does the mask look like? Is it just straight up 0 and 1? Wait, do we also transform? Shoot. What if I deleted this? What's gonna happen? Shit. I actually did not even look at that. Okay. Interesting. Okay. Seems like adding 0.5 and multiplying 0.5 is doing something. Seems like it's doing something with the brightness. Okay, let me experiment with this. Get image. Let's do train. Okay. Nothing happens. Oh. Mode is equal to train. No. I feel like that should still. Okay, still nothing. Still nothing. Oh, that's why. Come on, please plot now. Nice. Nice. Train segmentation. So this is just 0 and 1. Alright. Then does that mean maybe we could plot our image? We'll call it our prediction image. So what happens? Let's just do a single epoch. So validation, prediction. Step must be greater than 0. Huh. Not entirely sure what that means, I'm not gonna lie. Wait. Let's print type prediction. I feel like this is probably tensor. Oh no, oh no. Wait. Prediction type. And then let's print this baby out. So it is a tensor. Alright, so we have a prediction type. Now what about the prediction size? Oh shoot, I gotta register for classes too soon, man. Okay, shit. prediction.size. So maybe what I need to do then is permute this back. Dot permutes. I'm assuming that this is probably the reason why. So if it's 201, that means we're gonna need to get one, 2, 0 height width. CPU. Can call numpy on tensor that requires gradients. Use tensor.detach.numpy instead. Not entirely sure what this means. Okay, I'm gonna ask ChatGPT if it has any. What does this mean? So I'm curious to why this is being converted into an numpy array. NumPy.transpose. Plot image. I guess IM is a numpy array, so I'm going to have to switch it back. Okay, so maybe I'm going to try this. Dot detach dot numpy. Alright, let's see. Oh no. I'm curious to see what's going on here. Interesting. Yo. So plot the prediction image. Okay. So if my assumptions is correct, then I wouldn't need to do anything here with the no-grad stuff, because it seems like with torch.nograd, so whatever the gradient that's required for this shouldn't exist. Nice. Nice. Okay. This is cool. I'm not Yeah, I'm curious as to why the single, like if we have a single channel here, is, yeah, I'm kind of confused on how we're getting, how should I say this? How we're getting this to be black and white right now, like a grayscale image. I'm gonna be honest, I have no clue how it's doing that. I have no clue how it's doing that. So I think now is probably a good stopping point. I'm gonna go for a run, but was able to get at least the forward propagation thing going. The one thing I still have no idea what is going on here is okay, so maybe I'll add some questions here. Why is this grace scale? Is it the channel? Is it the single channel? Right. So do I need to transform the data sets or image to normalize it? Oops. Oh, shoot. Okay. So, right, the model is not training. Why? Okay, so no, okay. I guess probably don't need to transform the image then. Okay, so maybe tomorrow I'll look into actually trying to build out this convolutional layer, maybe using the architecture explained here to help guide me through. Oh, I see. So the reason they're subtracting, okay. Let me see where the plot is, or where the get image is going. Okay, so add multiply 0.5 and add 0.5 to reverse the normalization from self dot from self.img transform. Okay, so yeah, this multiplication of 0.5 is to unravel the standardization by dividing 0.5 from dividing each pixel by 0.5. And then we also add back because we have to unravel the effects of centering the image. And that's the same thing. Now the mask, I don't know. Okay, so the mask transformation is just resizing at 256 by 256. Okay. All right. So I'm going to save this, call this Mark 4 CMSC 472. Alright, so I'm going to save this for now, come back to it another time, but yeah, next stream probably going to have to work on some of the assignments from my other classes, so I'll get back to that. Alright, thanks for tuning in, and I'll see you guys in the next one. Peace.